Okay, if you're at two H's and one O, one O is 16 and H is 1 and 1, 2. So 2 grams of hydrogen for every 16 grams of oxygen. Or if we want to make a small ratio, 1 gram of hydrogen for every 8 grams of oxygen. And he discovered that, and he was the first person to think that compounds can only be made one way. All right, and they came up with this idea of a formula then, didn't it? All right, let's go on down. The next person you see, the next scientist, look on this page right here. It says Dalton's theory is about 1808, and he still thought the atom was kind of like a ball, though. Kind of like a ball. And then we have here, here is a person, where is it? See, I'm pretty sure there, this one right here, I don't know why he didn't have his name on here. Here it is. Okay, this one is William Thomson. William Thomson is also known as Lord Kelvin, and he did a lot of science. He was actually knighted. That's how much contributions he gave to England. And so he said that, let me talk about him. Let me see. Okay. I better go to J.J. Thomson first. Let me back up. I'm sorry. Let's go to J.J. Thomson first. Remember I told you that this is kind of weird that you would have somebody, hey, make me this piece of glass and put metal in it and put wires in it and give me a nice, really nice battery. And why? Why do you want to do that? I think something's going to happen. How do you think something's going to happen there? So when he did hook it up, something did happen. There was a beam that went through there, and you can actually see the beam. And he, as a scientist, said, well, I wonder what the properties of that beam are. And so he put a electric field here, and here's a negative, here's positive, and the beam was deflected or attracted here. It was deflected away from negative, attracted toward positive. He didn't know what that beam was, but he said, I think it's a bunch of negative particles. Now later then, what would we call those? J.G. Thomson is given credit for discovering what? The electrons. So that opened the door because all of a sudden, wait a minute, the atom's not this little ball of nothingness. This atom has something that's smaller than the atom, subatomic. There's a subatomic particle. And if you can get the negative things off of an atom, then why are atoms neutral? If they have negative parts to them, how can they be neutral unless they have what? Positive parts. And then people start saying, well, where is that? Where are the positive parts of the atom? All right, so let's go back here. So J.J. Thomson, electrons, and then we go over here, William Thomson here, the idea that the atom might be like a plum pudding, and that's called the plum pudding model. And he said, I get it. Imagine the atom's kind of like gooey stuff, and that's all positively charged, and the little raisins are the electrons. And if you do it just right, you can get the raisins to pop off. And now that's our model of an atom. Okay, so, and that was a good model for a while because nobody else could say that they knew of anything else. And then here is the hero, in a way. This guy's named Ernst, you like that? Name your child Ernst. Okay. But his name is Rutherford, and this is Rutherford's gold leaf experiment. And this is what he called classic. And the whole thing could fit right here on this table, okay? No electronics, no computers. And so here's what he did. Do you ever see this box? Ever look at that box up there? Some neat stuff was happening in science in the late 1800s. They figured out that certain rocks, not this one, luckily, but certain rocks that you could find, that if you put them somewhere like with a mouse, the mouse would die. If you had certain chemicals in there, they would start to glow. Something was being given off by certain rocks. And nobody knew that before, and that was called radioactivity. So nobody knew about radioactivity till the late 1800s. And they knew that there was something happening to atoms to give off this something. Well, one kind of radiation, have you guys heard of radioactivity? Okay, one kind of radiation was called alpha radiation, and they later figured out that what happened is some atoms, and you may not like this, that's okay, like uranium. Uranium is radioactive. As a matter of fact, one of the isotopes of hydrogen is radioactive. We haven't talked about isotopes yet, but let's take uranium. If you had a lump of uranium or radium and you sat there, you wouldn't see it. But if you had a certain chemical, it would make it scintillate. It would glow. And it also could kill you. The Curies, for example, did a whole bunch of experiments on radioactivity. And Marie and Pierre Curie, they were husband and wife, I'm sure that both of them died earlier than they would have. And, of course, they passed that information on to the next people. And then Rutherford would have known, if I'm going to take a piece of uranium or radium, I'm not going to have it sit there in my desk. You got that? So what's he going to put it in? A lead box. Why lead?
Because the lead attracts radium.
It does. It's very, very dense. And almost no radiation can escape from the lead box. All right, so everybody okay on this? So now you got this little box. It's got the radium inside there. And then they knew that there were these little things that were coming off, and they called them alpha particles. Alpha meaning the first. And they found out that an alpha particle was made of 2 protons and 2 neutrons. So 2 protons and 2 neutrons. Okay, so imagine these alpha particles that had a positive charge, and they're going all over the place. What I do is put them in a box, make a little hole there, open the door, and when I open the door, the ones that are going this way get trapped in the box. The ones that are going this way, I make a little beam. You can't see the beam, but I can put a chemical. I can put a chemical on this little screen here, and I had a little microscope, and I go around here with a little lens, and I say scintillate, 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 and I can actually figure out what's going on, where the radiation is going. Now, imagine not having a piece of gold there, and all the beam is going here. So there's all the scintillations happening right there, nowhere else. That makes sense. But then they took a thin piece of gold. Yes, it was thin. But put a thin piece of gold, and it should have blocked the alpha particles. But what happened? Have you read this yet? All right, you got almost the same number of scintillations as if you didn't put anything in front of it. It's like, why didn't the gold block the alpha particle stream? And he said, I can't figure it out. If it's like the plum pudding, then my positive bullets would have run into plum pudding all over the place. And what happens when positive meets positive? It would have been deflected, wouldn't it? All over the place, everywhere. Almost none of them should have gone straight through. And Rutherford said, the only thing I can tell you to explain this is that most of the atom must be what? Nothing. Most of the atom's volume is like nothing. But then, did any of them deflect? Yes. And some of them deflected even straight back. Not very often. And some of them deflected over here. And he said, my theory is that the atom must be mostly nothingness, but there's a very, very small nucleus that has what charge? Positive. Because it deflects my positive bullets. It's the first time anybody thought that the atom had a nucleus. And today we still believe that, don't we? So that was a very pivotal experiment they did. Can you guys eat lunch together or something? Save him a seat, okay? All right. Anyway, I forgot to tell you the name of this J.J. Thomson thing. It's called a CRT, cathode ray tube. I want to mention that to you because it might be an extra credit question, but you guys, not in your lifetime, but in your parents' lifetime, did you know that televisions used to be like this big and this wide, like that? And if you've ever seen some old TVs, you know they're big. How about a computer monitor? Look, very flat now. Huh? What did your parents have? Well, boom, okay? And so what happened is TVs and computer monitors are called CRTs. And what they actually did was a beam of electrons would shoot toward the front of the screen. And it was a vacuum tube. The television tube was a big vacuum. And so you could shoot that electron over here to the front of the screen. It would make the front of the screen either glow or not glow. And if it's a black and white TV, that's your grandparents, then you could actually control the electrons with magnets and say, and it'd go like this. And it would say, glow, 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 glow. It would make a picture many times a second. Oh, no, that couldn't be. Yeah, Yeah, that's what they did. And then when they wanted to get a color TV, they had 3 electron guns shooting at the front, and one of them was for the little red dot, and one was for the green, and one was for blue. And whatever combination you want, you can make every color you can think of like that, and that's how they made a color TV. Same thing with the old computer monitors. I even have some here. If we have time, sometime this year, if we have a day where Miss Plasman, she says, hey, what can we do? It's kind of fun. I can bring a sledgehammer and a great big tarp and goggles, and I can take some of these old TVs and we can hit them with a sledgehammer. And what would happen is, because it's a vacuum, there's lots of air here, there's no air in there. And when I hit it, it won't explode, but it will implode. And when it implodes, though, sometimes it'll push glass inwards, it hits the back, and sometimes it comes out. But it actually goes boom, it'll make an implosion sound. So anyway, I just want to show you that we don't have too many CRTs anymore. Sometimes you'll see them on the side of the road. Even Goodwill will not take them. Goodwill will not take your old TVs like that. And so now you got to take them to a special place to get rid of them, or set them on the side of the road. Sometimes people take them. I sometimes take them. All right. Also, the TV has to have been working for me to have. I know the vacuum is still good. So if you want to do that at home, you tell your parents, you wear safety goggles. Maybe they would let you do it. But all right. Well, I think what I'm going to do is I'm going to stop the scientist for right now. I know. There's one more. I hate this because when you're looking in the book for scientists, you read and you read and you say, wait, okay, proton. Okay, then wait, and then look, turn the page. This little tiny thing here. It didn't make it on the last page, did it? So what was the last scientist that was mentioned in the book? And his name was what? Chadwick. And there was something wrong. There's something not wrong with the idea that the nucleus had protons. Nothing wrong with electrons, but there was something wrong with the mass numbers. It seemed like there was more mass in the nucleus than just the protons would account for. And so he said there was another particle, and that was called the neutron. Okay, is everybody okay on that? All right. And the last thing, as far as a little mini review, is remember that if you looked at numbers, here's a typical atom, and the diameter of the atom is 10 to the minus 8 centimeters. That's 10 to the minus 10 meters. Let's say that's an angstrom. Anyway, if that's 10 to the minus 8, what's the diameter of a typical nucleus? 10 to the minus 13th. And what is that? How many times smaller? How many powers of 10 smaller is the diameter of the nucleus?
10 trillion.
And 10 to the 5th is 100,000. So the nucleus is 100,000 times smaller than the diameter of the atom. Now the problem with this is, if you try to draw that in a book, you're trying to teach kids about a scale model of the atom, you can't. If I draw an atom this big, you'll never see the nucleus. I'd have to make it 100,000 times smaller. Can't see it. So we build a model in a science book that makes it bigger than it really is, so at least you can see it. And the model I'm going to use in my handout sheet is even bigger than that. Yes?
Is it like a soccer ball on the Earth?
We could make a different analogy. I think the soccer ball would be too small compared to the Earth. But here's the analogy I have heard. You go to a Major League Baseball stadium, okay? You go to second base, and you put a little green pea on there. And you put a green pea on second base. And then the electrons are going to be past the home run fence. So the whole stadium is an atom, and the little pea at second base is a nucleus. I have heard that analogy.
Wow.
So most of the atom is empty space. All right, good question, and that's the only analogy I remember. We could probably make up some other ones though. Just find something that's 100,000 times bigger. All right.
What about like a bowling ball?
Well, again, I'd have to sit and do a little mathematics to say what's 100,000 times smaller than that. would I still be able to see the nucleus if I made it? So you measure the bowling ball, divide it by 100,000, and then try to make something like a grain of sand. Is that too big? You could try that. So if somebody wants to try that as an extra credit thing, you would do some measurements, show the mathematics, and say, here's an analogy of an atom and an electron. You could do something like that. Okay. Now let's go ahead, and if you'll get your handout sheet that I gave you, we're going to start changing gears a little bit here. This is, I really like teaching this part. Does everybody have the handout sheet? Okay. I'm going to, I hope that I can teach you something that was not taught to me. I'll be honest with you, okay? In high school, every time they used the word isotope or ion, it was always a matching vocabulary. And all I had to do is know is that when they said something about blah, 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 and it has a charge, all I had to do is write the word ion, and I got it right. Blah, 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 same element, different mass. If I saw that, I just put isotope, and I got it right. Now, did I understand what an isotope and ion was? No. So here I am going to college, and I really do want to be a science major, and so I'm taking biology and chemistry the first semester, and doggone it, I couldn't believe the chemistry teacher over and over and over using the word ion, isotope. And then I go to biology class, and they're talking about experiments done with ions and isotopes, and oops. Okay, so what happens? Do you think I understood the lesson that well? I didn't. So I've always taught this in the manner that I'd like you to understand what it is. I had one year, this is a great story. I was at Grimsley, and they had a student teacher, not my student teacher, and you don't get to pick them. They just say, hey, will you take a student teacher? And so another teacher had a student teacher, and I had some students, and I had actually taught this to them in biology, and they were taking chemistry, okay? And I didn't ask them. About 3 or 5, I don't know, 5 of them came over and went, well, Miss Feeney. They said the blah, 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 blah. She said blah, blah, blah. And I said, well, okay. She just started teaching, just like me. When I first started teaching, I didn't have everything down. And she was teaching them the wrong way on what an isotope and an ion was. But a year after I taught it to them, they knew something was wrong. So I'm hoping that's going to happen to you, that you'll remember this. And if you go to college and you're a science person, you'll remember these things. Is everybody ready? Okay. All right, here we go. Here's what I think is going to help you more than anything else. We're going to talk about subatomic particles. What are atoms made of, all right? But here's what's going to happen. If you can separate the world of mass from the world of charge, don't try to blend them. That's a brick wall, by the way. If you can build a brick wall in your mind and say, let's talk about the world of mass. And then you cross over the brick wall and say, now we're going to talk about the world of charge. If you can keep those two worlds separated, you'll always know the difference between an ion and an isotope. So you have to trust me, okay? Everybody ready? All right, here we go. When they did studies, and these are mainly physics people, they found out that protons have a mass. Protons have a mass, okay? Now, I don't memorize, I'm not a nuclear physicist, so I don't memorize this number, and I don't ever use it. So I'm going to ask, here we go. All right, here we go. Ready? What is the mass of a proton?
Should we all look?
Oops. Wait a minute.
You should have erased 2 others.
Yeah.
Wait a minute.
What is the mass of a proton?
What is the mass of a proton in grams? Huh?
We should all give our guesses.
What? You give a guess?
Yeah. And then numbers closer. Yeah.
Okay, really?
Yeah.
All right, that'd be interesting to me. You want to guess?
Yeah.
What do you think?
I'll start. 0.001.
Wow, grams?
Yes.
All right, not a bad guess. Anybody else want to guess?
0.0000003.
How many zeros?
Yeah.
1.6726.
10 to the negative 15.
All right, wait a minute. What is it?
10 to the negative 24.
What is it?
That was just a guess.
What is it? 1.67 what?
26219 times 10 to the negative 24.
You just ruined the whole game, Tim.
Okay, that's a great guess. And so let's take a look here. Here's a number that has a decimal point, 23 zeros, 1679. Is that what you said? Now, I don't memorize that number, but you were way off. So the number of grams a proton weighs is incredibly, incredibly small. You got that? So being a person, scientists are real people, you know that? They could have used that number over and over and over again, right? They could have, but they also were a person. Here's what they did. I hereby declare that that many grams is now called 1. Not 1 gram. No, we're going to make up our own mass unit. I'm going to call it 1 atomic mass unit. 1 AMU. Don't ever tell me that the proton has a mass of 1 gram. A paperclip has a mass of 1 gram. There's no way. So it is 1, but not 1 gram. What is it? 1 AMU. Okay, pretty easy? That makes it pretty simple. You know, astronomers, you know the average distance from the Earth to the Sun is about 93 million miles? And I could say that number all the time. But then you know what most astronomers say? 1. The distance from the Earth to the Sun is 1. 1 AU. 1 astronomical unit. And if you're a planet that's 13 AU, you're 13 times further from the Sun than I am. Well, I kind of like that. See? They're real people. They think about that. Let's go to down here to neutron. I'm going to jump to neutron right away. The neutron, oh, by the way, where are protons found? I forgot. Okay, in the nucleus. Okay, now, if you are in the nucleus, you're called a nucleon. A nucleon is any kind of particle that's found in the nucleus, and a proton is a nucleon. And here's the other nucleon. The other nucleon found in the nucleus is the neutron. And its mass for this class, if you become a particle physicist, you'll know there's an incredibly, incredibly small difference. But for this class, it is also 1 AMU. You okay with that? Now, all right. Some of the things they do when they got, I gotta watch my time here. When they were started, I call splitting atoms. When they started making particle accelerators and slamming particles into other particles and see what happens, they would see one particle collide with another, and they'd use some mathematical equations in physics. And he said, just like today, if you get in a car accident, the police can actually figure out how far your car went after you hit something. They can put it. They're not physics people, but they go back to their thing and put it in a computer, and they'll say you were going 80 miles per hour, and they knew what make and model your car was and that kind of stuff, and what conditions the roads were, and you say you were going over 80 miles per hour. How did you know? Yeah. And so they weren't there, but they have the evidence showing that was that speed. So here we have evidence of collisions showing that that's how many grams you are, and we're going to call that 1 AMU. Let's go over here now. I can't remember. The last time I looked, it was probably this number here. And it's 1 over 1,866. I'm not going to have you memorize that. AMUs. Now, it just so happens that, let's take a look here. Calculator. 1 divided by 1,866 equals. All right. This equals 0.00053 AMUs. Now, the reason I even put that down there is, boy, you better have, okay, thank you. Thank you, there you go. I got all this mess here. Okay, the reason I put that number down, you don't have to know it, but if I had 1,000 electrons, then it would still only be 0.5 AMUs. Well, tell me what element has 1,000 electrons? None of them. As a matter of fact, the number 118 only has 118. So what I'm saying is that for our purposes, the mass of the electron is 0. We'll never have enough electrons in any atom to say that that's adding anything significant to the mass. So if I ask you to think about the world of mass, then you are thinking about the world of the nucleus. And 99.999% of the mass of the atom is in the nucleus. So if we start talking about the nucleus, we're talking about the world of mass. All right, let's go down to a drawing here. And again, way out of scale. Way out of scale. But I want you to be able to see it. What do I notice here? I notice that in the nucleus are 3 protons. The number of protons is always your atomic number. And I'm going to tell you right now, the atomic number 3 belongs to only one element, lithium. There's no way that this is not lithium. Go anywhere in the universe, if you find an atom with 3 protons in the nucleus, it's lithium, period. Lithium wasn't number 3 because they were pulling elements out of a hat. Who gets to be number 1? No. Hydrogen's number 1 because the only kind of atom that has only 1 proton in the nucleus of every one of its atoms. Yes? Okay, next. What is the chemical symbol, Li? Li is always the atomic number 3. And then the next thing is the mass number. Now, watch now. The mass number is the number of nucleons. So you add protons and neutrons. Let's watch. Proton, 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 neutron, neutron. So what do you think?
7.
This one has a mass of 7. Yes. Now, watch now. Here's what I would do. If I wanted to communicate with you that I'm talking about this specific kind of lithium, I would write capital L, little I, and in the upper left-hand corner of the symbol that I'm going to write for you, I'm going to write it like this. See this? Li. I'm going to let you know that this one has a mass of what?
7.
Okay, so I'd write it like this. See that? This is called a lithium-7 isotope. So the world of mass is the world of the nucleus. It's the world of what? Isotopes. Now, look right here. What if I found another lithium atom with 3 protons, but it only had 3 neutrons? How would I write the symbol for that?
3 Li.
No, the mass number is how many total things in a nucleus. And this would be called lithium-6 isotope. You get it?
Wait, how'd you get that?
This lithium here has 7 things in a nucleus, and this one has only 6. So it has 3 protons and 3 neutrons. You get that? So what's the difference between one isotope and another of the same element? Not protons, neutrons, right? Okay. You okay? All right, make sure here. Now what I'm going to do here is flip this over, and we'll come back and finish that page here. I've drawn 3 completely different, would you agree these are 3 different atoms? They're different, right? Okay, see if you can fill in the box for me. Put the atomic number here, put the mass number here, and put the symbol right here. Let's try that. Put the atomic number, and then put the mass number, and then put the exact symbol there. All right, here we go. The atomic number is always the number of protons. How many protons do you have? How many protons do you have? How many do you have? The number of protons will always identify you. Number one, if you're atomic number one, you must be what? Hydrogen. Then what is this one? Then what is this one? What?
Yeah, isn't it?
But what is your mass number? What is it? Look at me. What's the mass number? How many? How many? One. Electrons do not involved in the world of mass. What's the mass? One. What's the mass? Two in the upper left-hand corner. The mass, 3. There we go. Everybody see that?
You have to put A in here.
No. Now watch. Atoms of the same element, but they have different masses, are known as what? Isotopes. Now here's where that student teacher made a mistake. And barely when I first started teaching, I don't think I knew it either at first. Which one of these is hydrogen? Which one of these can you make water out of? All of them.
No.
No, the second one.
All of them. Which one is explosive? All of them. They all act chemically like hydrogen. Which one of these would a bucket full of water be the heaviest bucket if you tried to lift it?
Tritium?
This one. So if I made water and I used hydrogen 3, it would be a very heavy bucket of water. This would also be heavy water. Now, it just so happens that many nuclei of atoms are very stable. And they kind of stay what they're supposed to do. They do what they're supposed to do, just kind of sit there, you know? But there's one of these which is not stable. One of these isotopes is radioactive. And I'm not going to talk about that too much in this class, but this hydrogen will actually give off part of its nucleus and change into something else. So I'm not going to get too much into that, but every element up here has isotopes. Everybody has isotopes. Most of them have stable isotopes, and they also have radioactive isotopes. Hydrogen only has one radioactive isotope. The other two are fine. They're not radioactive. Look at 83. See 83? 83 all the way to 118. If you're 83 or higher, there is no such thing as a non-radioactive isotope of you. There is no non-radioactive isotope of radon or uranium or neptunium. Every one of those. If it's uranium, it's radioactive. If it's hydrogen, maybe, probably not. This is kind of rare. Hydrogen's probably not going to be radioactive because you don't see that very often. And these are called isotopes. You get it? Now let's go back. Only got about 2 minutes to us. One thing I forgot to mention that when they put these, they said, I'm going to reserve this upper left-hand corner for the world of mass, the mass number. You get that? What did they save this bottom corner for? What's going to go here? The atomic number. What's that, though? It's always the number of what? Protons. Now, if you don't happen to have a periodic table, it'd be nice to put a 3 there to remind people that this guy has 3 protons. But look what you can do. If you have 7 things in your nucleus and 3 of them are protons, what can you do if you subtract those 2? 4 what? 4 neutrons. How many neutrons does this have? Oh, that's kind of neat. So if I have both of these numbers here, I can say the mass number minus the atomic number is equal to what? Number of neutrons. This guy has 4 neutrons. This has what? 3. Flip the page. Let's put the exact symbol here. I'll put a 1 to 1. How many neutrons do you have? Uh-oh. What? In fact, this is the only isotope in the universe that has no neutrons. This has how many neutrons?
1.
How many neutrons?
2.
There you go. See that? That's called the world of mass. If you can remember the world of mass as the world of the nucleus, and that's protons and neutrons, right? Then when I start tomorrow with the world of charge, you'll say, oh, I got it. I'll cross over the brick wall, and we'll talk about the world of charge.